and we're going to be working with circuits with independent voltage and current sources. The problem is to determine V sub 0 in the circuit shown below. The circuit has three independent sources, two current sources and a voltage source. We're measuring the output voltage, V sub 0, across the load resistor, a 4 kilo ohm load resistor in our problem. It's on the rightmost side of our circuit. So we're going to use loop analysis or mesh analysis to do this problem. So we instantly realize that we're going to be using Kirchhoff's voltage law as a way of summing voltages around each of the loops in our circuit. So the first thing we do when we have a problem and we want to solve it using mesh analysis is we assign loops or meshes to the circuit. And we also assign loop or mesh currents as well. So let's do that first. The first loop I'm going to assign is the upper left-hand loop, and I'm going to give it mesh current I1 going around in the clockwise fashion. We have I2, I3 below, and then I4 in the lower left-hand corner for loop 4 or mesh 4. So now we've assigned our meshes and we've assigned our mesh currents. That's the first step in mesh analysis. Then the second step is to go to each one of these meshes and to add up or sum up the voltages around the loop, the closed path, which we have starting at typically I start at the lower left-hand corner and going around the loop back to that same corner. So we'll do that for each one of our loops. We'll go all the way around it from start to finish, ending in the same point, summing up the voltages. What we're going to find in this problem is that we have a couple of issues with using this straightforward approach and doing the problem, so we have to use some of our additional rules of mesh analysis and Kirchhoff's voltage law. So let's start with loop 1, which is in the upper left-hand corner. We need to sum up the voltages around this loop. So if we start in the lower left-hand corner and we start up, we see that we run into a 3 milliamp source. We don't know what the voltage drop is across this, so we'd have to assign another variable, V sub 3 milliamps, for the voltage drop across it. So we'd add another variable in addition to our mesh currents, our 4 mesh currents, we'd have a fifth variable in that case. And we could go on around and we can find the voltage drop across the 2 kilo ohm with respect to the loop current I1 and I sub 2, and the 4K we could do the same using I1 and I4 in the current as to find the current through the 4K. But we have this problem with the 3 milliamp resistor, or 3 milliamp source on the left-hand side of the circuit. So we want to realize that when we're doing mesh analysis, what we're really after for the result from our analysis are the mesh currents, I1, I2, I3, and I4. Once we have those, we can find any other value that we want in the circuit, any voltage drop, any power, whatever else might be of interest to us. So that's really what we're after. If we look at this loop 1 and we inspect it closely, we see that I sub 1 is equal to 3 milliamps. So the problem itself gives us I1, and we don't need to determine I1 through a mesh analysis approach where we're summing up the voltages around mesh 1. So I1 is equal to 3 milliamps. Let's go to the second loop and see if we can come up with an equation for it. So starting in the lower left-hand corner, we encounter first the voltage drop across the 2 kilo ohm resistor. That voltage drop is going to be 2K, and since we're going clockwise, the current which is going the same direction as I2, it's going to be I2 minus I1, which is also flowing through the 2 kilo ohm resistor, I2 minus I1, because it's flowing through in the opposite direction of I2. And we continue on around the loop, and we encounter the 4 kilo ohm resistor, which just has a current I2 flowing through it. So the voltage drop is 4K times I2. And continuing down through the 12 kilo ohm resistor at the bottom of loop 2, the voltage drop is 12 kilo ohms times I2 minus I3. And that's our last voltage drop before we get back to our starting point in our loop that we had for loop 2, back to the lower left-hand corner of it. So let's go down and look at loop 3. If we look at loop 3, we encounter really the same type of problem that we did up with loop 1. But this time, we see that when we hit this current source that we don't know the voltage drop across, we don't have this current source assigned to just one loop. It is shared between loop 3 and loop 4. So we have an equation that we can write for that, and it will be that 1 milliamp is equal to I3, which is flowing the same direction as the 1 milliamp source, minus I4. So we can at least write that. So that gives us another equation, but we need 4 equations to solve this, because we have 4 unknowns, I1, I2, I3, and I4. So we need one more independent mesh equation in order to solve the problem. And so the way that we're going to do this is using the concept of a super mesh. In order to get around this 2 milliamp source, the 1 milliamp source in the center of these 2 loops, we're going to assign a mesh which we can sum the voltages around just like we could any other mesh, but is independent of mesh 1 and mesh 2 above, so we get another independent equation. So we've outlined our mesh in dashed red. And we can, again, sum up our voltages starting in the lower left-hand corner of this mesh. Going around this mesh, we have the ability to write an equation for all the voltage drops from start to finish. And this is, again, the super mesh. We use this concept when we have a current source in a mesh analysis problem that is shared between 2 adjacent loops. Whenever we have that the case, we have to rely on mesh analysis and super mesh analysis in order to solve the problem. So let's write our last equation for the lower 2 loops. So starting in the lower left-hand corner, we run into the negative polarity of the 6-volt source first. It's a minus 6 volts for that voltage drop. And then we encounter the 4 kilo ohm resistor. Since we're going in the clockwise fashion, I4 is also traveling the same direction through that loop. It's going to be 4K I4 minus I1. Continuing to the 12 kilo ohm resistor, it's 12K I3 minus I2. And then continuing, we run into the 2 kilo ohm resistor with only I3 flowing through it in the same direction that we're summing the voltages. So we have 2K times I3. And that's our last voltage drop before we get back to the starting point. So that's equal to 0. So now we have 4 equations and 4 unknowns. What we're really after in this problem is we're after V sub out, which is the voltage drop across the 4 kilo ohm load resistor. We know V out is equal to 4K times I sub 2. Passive sign convention tells us the positive I2 would flow into the positive of the voltage drop across the 4K resistor. So it's 4K times I sub 2 for V out. So really the only loop or mesh current that we're interested in is I sub 2. So that's the one we're going to solve for. And if we solve for I sub 2 from these equations above, we get an I2 equal to 31/15 milliamps. Now if we use that and plug it into our equation for V out, then we get a V out which is equal to 8.27 volts.